I'm going to try to do in an hour, between an hour and a half, an overview of the first part of this textbook. Okay? The first part of it covers optical fibers. The second part covers the transmitters and the receivers. That's the lasers and the photodetector systems. Okay? So maybe we'll get to that some other day, perhaps in a few weeks. It's up to Professor Sheridan. Now the whole thing comes together and gives us fiber optic systems. You can see here, if you can, there's a tiny optical fiber just there. Okay, there's the optical fiber. That's about 125 microns diameter. And here, I'm pointing now at the laser. That's a semiconductor laser sitting on a gold submount. So this is and then that's on a larger mount again. So the semiconductor laser, you can see, is also of the same order of magnitude in size. You know, 1/10 of a millimeter each side of it. Okay. Typical power out of those type of lasers is maybe between 5 and 10 milliwatts. That's more than sufficient to communicate over 10 or even 50 kilometers of optical fiber, and still have enough left over at the receiver. But that part of the aspect of it is being done in part 2. So why don't we just start and find out why you want to use these the optical fiber. A lot of people are on the impression that when they use their mobile phone that they're actually speaking over microwave to Mammy out in wherever she is. But you're actually speaking for over 90% of the way over an optical fiber. As soon as your microwave signal reaches the nearest antenna, in this case probably just down there at the RTE corner, goes into the optical fiber backbone network, which is connected by fiber worldwide. And it's in the future, and it will be possible to actually route your data, with your IP packets, using all optical devices by inserting diffraction gratings into the optical fiber. You can already do that, but it's becoming more and more widely deployed now. And you can have passive routing of the data. I'll come to that at the very end. So why optical fiber? Microwave at, say, a 1 gigahertz carrier. Say you want to supply customers with 100 megabits per second. Divide one into the other, you get approximately 10 customers. The optical infrared signal is at 200 terahertz. We'll do that calculation in a minute. Divide again 100 megs into 200 tera, and you get 2 million customers. So with an optical fiber network, you can supply a complete city with the microwave, maybe an office-wide Wi-Fi network. Now, the point about using the glass is that even though the subject was approached 150 years ago by an Irish scientist, Tyndall showed that you could trap a light beam inside a tube, glass tube. But the glass of that time was the kind that's used in window panes, for example. And if you try to make a window pane 100 meters thick, not mind 10 kilometers, it would be perfectly dark inside in your room, because industrial glass of that nature has an awful lot of impurities in it. We need to get the impurities in the glass down below parts per billion. Okay, molecule of impurity per billion molecules of glass. And to do that, we have to actually use semiconductor technology. Just as Intel down there in Leaslip are making silicon chips, we adapt the same technology to make silica fiber. Because we can then take, for example, using the semiconductor kind of technology, we can take a glass carrier case like that, okay, and inject carrier gases. One of them carrying the silicon, and inject oxygen as well. So the silicon carrier is called silane, SiCl4, and reacts with the oxygen to produce this. They started doing this kind of work in the late 60s, early 70s, so it's 40 years ago today. And also in places like Bell Laboratories in New Jersey. That time, Bell was the main telecommunications operator for the whole of the United States. So the Bell Labs are famous for developments in this area, but also in places like the University of Southampton and other places. So we inject carrier gases into this, and meanwhile we keep the whole thing hot with a flame, and they found it convenient to use a conventional lathe in the beginning. So this was mounted on a lathe and rotated. The gases were injected, the whole thing was kept hot, and by chemical vapor deposition, as with growing silicon chips, you deposit the silicate inside. And after perhaps a couple of hours, we end up with what we call a preform. And the preform would look something like that, and of those dimensions as well. So if you take a preform like that, and say it's 1 meter of the order of a meter, and of the order of a centimeter across, it's a simple cylinder calculation. You can stretch that out into 10 kilometers of our 100 micron fiber. And for once, when we try to turn the preform into a reel of fiber, nature is on our side. Because you mount this up on the top of a tower, and again you heat it with perhaps a radio frequency heater, and you draw a thread. Draw the thread down onto a reel and keep turning the capstan reel at a perfectly constant rate. And you'll end up with 10 kilometers of the 100 micron fiber. But where nature is on our side is whatever kind of refractive index pattern is in our preform reappears in micro miniature in the fiber. Okay? So if we have, while we're injecting the carrier gases in the growth process, we also inject dopant gases like phosphorus and boron. But this time it's not to create a p-type doping or an n-type doping, it's to very slightly adjust the refractive index. So while we grow the layers of glass in the preform, we can produce a profile. The refractive index could be high in the center and lower at the edges. And that profile is mimicked when we draw the fiber out into a reel. So I'm going to use that symbol, it's widely used, to represent a 10 kilometer span. It doesn't have to be on a reel anymore, but this could be Lucan, and this might be Andrew Street Exchange, for example, in the city centre. So 10 kilometre span of fibre. TX is our transmitter, RX is our photo detection receiver. Let's say we're transmitting data at 1 gigabits per second. Okay? I mentioned, by the way, as a sample, example, there are 100 megs to divide into the carrier frequencies. And as you know, they're only beginning to offer something like 40 megabits per second per broadband customer here in Dublin right now. I see UPC are putting in new fibres all over the place to offer that. But it won't be very long before people want a lot more. Already in places like South Korea, they're offering customers 1 gigabit per second. And that's not far off here either. That can't be. So 1 gigabit per second, that means that these pulses are 1 nanosecond long. Okay? And by the time they travel the 10 kilometers, the 1 nanosecond pulse has spread out a little bit. Dispersion. And the next pulse is a 0, and then the following pulse is spread out again. So what we had as a 101 data stream becomes 1 question mark 1. We have the opportunity here for making an error at the receiver. The difference between the ones and the noughts has become so diminished. Meanwhile, the height of the pulses is also reducing because we still have a small amount of impurities and a small amount of scattering in the fibre, so that the losses occur. Okay, if this process is taking place, we call this inter-symbol interference. The ones and the noughts and the ones are interfering one another in our decision circuit. It is agreed that due to this process, there should never be more than 1 error in a billion. So bit error rate must be less than 10 to the minus 9, 1 in a billion. If you look at that, when you're sending 1 billion bits per second, that means you're getting 1 error every second. So it seems like a stringent requirement, BER of 10 to the minus 9, but it actually can be severe in certain quality situations. For example, banking. If you're withdrawing 100,000 from your account and there's one error, it might turn out to be 1 million. So for certain telecoms applications, and even higher quality than that, financial institutions might require 10 to the minus 12, but they pay more to the provider. Right, I talked then about the profile of the index in the fibre mimicking the original preform. Typically, we would use a step index fibre of a design something like this. Here we have the axis of the cylinder, that's the optical fibre, and the refractive index of glass 1.5. Initially, we would have injected some boron or phosphorus or some dopant to slightly diminish the profile, the refractive index. So out in the edges, we call this the cladding, the refractive index there is 1.49. It's less than 1% lower. And that's all it takes to trap the light. All right? You could say, let's just have 1.5 index for glass and outside you have air. And then you would get total internal reflection, sure. But the trouble is you'd get a huge amount of dispersion, as you'll see from this calculation. So by adopting the core and cladding approach with less than 1% variation in index, it means that only rays that strike the boundary at less than the critical angle, C, there it is, C, okay, will be totally internally reflected. Okay, now we just use Snell's law. The N1 over N2 is sine of one angle over sine of the other angle. So we can get, the other angle is 90 degrees and this inner angle is critical angle. Do the calculation and you can see what the critical angle is in this particular step index fibre design. Now if you trace it back, that's C, this is 90 minus C, you can apply Snell again at this boundary. Now we are going out into air, so the calculation will involve a 1 index for air and 1.5 for the glass. Repeat the calculation and the aperture, as we call it, is 13 degrees. So it's a pretty small aperture. Now that's very important. That aperture means, being very small, it means that there isn't a huge difference between these rays and the rays that go all the way down the axis. The fast route and the slow route, there isn't too much difference. So there isn't too great of a dispersion. All right. Secondly, the angle for A is very small, which means if we combine, we want to splice two fibres together, they must be very, very accurately aligned. Or, if we put an optical connector on this, and another one, the connectors must mechanically align with very great precision. I'm reminded of an incident that occurred, I think it was about a year ago. CERN were carrying out collisions with neutrinos, and the neutrinos were being detected several hundred kilometers away in an underground laboratory in Italy. And if you remember, the headline is Einstein's theory disproven. And the whole theory of relativity, that it was just keeping the modern telecoms world together, including satellites in orbit and all the rest, seemed to be wrong, because the neutrinos were arriving, I think it was about 1 billionth of a second too soon. It must have been exceeding C. And Nobel laureates around the world were at their blackboards sending out messages, it must be this, it must be that, it must be the anything but we can't break Einstein's theory. In the end, and all of them were discarded one after the other, and in the end it turns out, I believe it was an optical fibre connector in the equipment, wasn't fully let's go on. So another problem, as I said, apart from the dispersion, which causes bit errors, is the loss in the fibre. Okay? Now, this spectrum shows you visible light, infrared, near infrared in fact, and then going out into the longer infrared. I should say that all of the diagrams in that book are designed to be redrawn, and that's why I'm using a flip chart today instead of PowerPoint, because I've just redrawn these this morning just to show you this is what you have to do. Because when you redraw the diagrams, you learn all the data, you learn its significance, and you memorize it. Okay, so the last spectrum of SiO2 consists largely in the ultraviolet of scatter. Okay? And as we go from blue light at 300 nanometers to red light at 700 nanometers, we have doubled the wavelength. With Rayleigh scattering, the loss reduces by 16, because Rayleigh scatter depends on 1 over lambda to the 4. So we have a 16 factor drop as we go through the visible spectrum. Then we can double it again, 700 nanometers red, out to around 1.4, 1.5. We have another factor of 16 reduction in Rayleigh scatter. This is the same process that makes the sky blue. The shorter wavelength, the blues, are scattered in the atmosphere, which makes the sky blue, and the reds come further down to Earth. However, as we pass beyond this region around 1.55 microns, a number to remember, the glass molecules begin to vibrate and absorb. So we get molecular absorption. The minimum wavelength for SiO2 is here, 1.55. Now, the early fiber optic systems actually used around gallium arsenide lasers, around 850 here, because they didn't have any other lasers at the time. And as time went by, they developed ternary lasers and then quaternary lasers. Quaternary lasers consist of indium, gallium, arsenic, and phosphorus. Okay? So the wavelength of use moved further and further out and closer to the last minimum as the decades went by. This is the region we operate in now. Now it turns out, apart from those two processes I talked of, you can never get rid of all of the water. There's always a small bit of contamination. Those carrier gases, it only takes a few molecules per billion, and there's enough water left for the OH bond to vibrate. And that causes a peak absorption around 1.4. So the water peak separates the S band, what we call the short band, from the C band, or conventional band. All your telecom systems today operate here. Early, 25 years ago, they operated here because we didn't have lasers for the C band. Today, still you'll find local area networks using the 1.3 micron band, but not the backbone intercity and international fiber optic networks. So there are the numbers to remember, the last minimum, the local minimum there. Now another one of interest is silicon. Silicon cuts off at 1.1. It's got an energy gap of 1.1 electron volts, and by pure chance, if you do the calculation, that also converts to 1.1 micron wavelength. So you can't use silicon detectors out here in the S band and neither in the C band. We have to use quaternary materials as well. Okay, so do your calculation for the 1.5, divide it into 3 by 10 to the 8, and you'll get the figure we had earlier on, 200 terahertz is our optical frequency. Right, our basic primitive fiber was a step index. In the core of the fiber, the index was 1.5, and then it jumped down abruptly in the cladding to 1.49. That was a major advance because it reduced the aperture and it increased the critical angle, making less difference between the fast rays and the slow rays, much less dispersion. But is there a way to improve on that again? Well, here's our fast ray going close to the axis, so it's called a paraxial ray. And here's a non-paraxial zigzag ray. And you ask the question, what can I do to speed up the slow rays? get them closer to the speed of the fast rays. And of course, immediately you think the velocity of light is constant over the index. So the only thing you can do here is reduce the index. If I can reduce the index, I can increase the velocity. Now, these slow rays are spending longer near the edges. So as we approach the edge, I should gradually reduce n. That will speed them up. So here is our old fibre, step index, and here is our graded index fibre. Notice the difference, the improvement there. The bandwidth distance product here is 0.03 gigahertz times kilometre, and the bandwidth distance product there, both those factors are crucial. The bandwidth and the distance you can go. The product is around 1,000. So it's well worth our while to find a way to make the graded index. Now, from the point of view of growing that thing, all we've got to do is make sure the preform, as we inject the gases, what we need is a computer-controlled set of valves. And we write a program to open and close the valves in such a way that the dopant gases gradually change the refractive index at a desired rate. Okay? So that would make a very nice, it would have made a very nice PhD project somewhere like the University of Southampton 20 years ago. The question is, if I want to program the valves, the computer for the valves, what rate must I reduce this pattern? Now, one way or the other, what we often do is we turn the index pattern on its side and just show n is a function of r. N1 will be from now on the index in the core. It's a function of the radius. It's gradually falling away. And when we reach r equal to a, it flattens out at the value n2. Okay? So this was the challenge, as I said, those couple of decades ago. And some of the researchers in Bell Labs in New Jersey came up with a formula that they said looks pretty good to us, and it was adapted worldwide from then on. If we have a graded index profile, Glogan Marcatilli said let n of r be equal to, that's n1, it's the same down here, n1, and let it fall away. So 1 times n1, that's in the axis, falls away as we go out the distance r at a power gamma. So here we have 2 minus a constant, r to the power gamma over a constant. A is the radius of the core. Okay. Now you can see when r equals a, that's a over a, which is 1. Okay, so you just get 1 minus 2 delta. Square root of 1 minus 2 delta. So when you reach a and beyond, the bracket disappears there. They called gamma the shape factor. It's the refractive index profile shape factor. How fast is the gradation of the profile falling away? If you put gamma equal to infinity in that, you get a step index fibre. You can see that if you just look at it. No matter what r is relative to a, right, it's going to be a fraction, and any fraction to the power of infinity is 0. Right? So it's just going to be n1 in the core, and then n1 minus this amount in the cladding. Okay. Conversely, if you put gamma equal to 2 in that formula, the profile is falling away at the rate minus r squared. So we've got a parabola. And then you can have all the values of gamma between 0 and infinity. And the question that these guys would have set for a bunch of their PhD students in the Bell Labs was, can you go away please and find out what value gamma should be when you've got your PhD? And actually, what they found was most surprising and well worth a PhD. Because at that particular value, gamma equal to 2, when you put these equations, and I'll show you in a minute how to do that, when you put that equation into the wave equation, and solve for the guided light in the fibre, you can measure the dispersion. In other words, you can measure how fast is the fast ray propagating, how fast is the slow ray propagating, what's the difference, and now we've got the dispersion. And you can keep doing that over and over again for different values of gamma. Here is the result. Gamma is increasing towards infinity, so step index is way out here on the right. Gamma is equal to 2 here, and at that point there was a very sharp cusp. And make a note of the axis on the left hand side. That's 1/10 of a nanosecond per kilometre, 1 nanosecond, 2, 10, 100 nanoseconds per kilometre. Our pulse that we inject is spreading out every kilometre by, say, by a nanosecond. And if we had our gigabit stream, there'd be total overlap of one pulse and the next one. It'd be useless. However, by this time, the fibres that were being installed in places like New York City and San Francisco and beginning to be installed in places like Dublin and London would have been step index fibre. And these guys took a look at their results and they said, my God, there's a factor difference of 10,000 or even more, between 10 and 100,000 if I use graded index parabolic fibre. Straight away, if I can grow that kind of fibre, my bandwidth distance product increases by up to 100,000. Notice that if you take the amount of nanoseconds spreading per kilometre and turn it upside down, nanosecond becomes gigabit and per kilometre becomes times kilometre. So the inverse of that quantity is the bandwidth distance product. It tells you how many gigabits per second you can use and for how long a span before you have to repeat the whole thing all over again. Go into a detector, square it all up again, equalize the whole thing and put it back out through another laser. So we keep that in mind, that inversion relationship. Also we'll keep in mind that in the Globe and Marcatilli formula they jumbled N1, N2 altogether into this delta factor. I've written it there. The value of delta by their formula was N1 minus N2 over N1. So that would be 1.5 minus 1.49 over 1.5. That's less than 0.01. It's a fraction. It's less than 1%. So delta is a tiny number. It's a measure of the difference, relative difference of the index between the core and the cladding. Okay, well, I said that the students working on this were asked put the gamma value into the wave equation and calculate the modal dispersion. The question is, how did they do that? So, now our primitive method of finding dispersion so far was the ray approach. And we took a kilometre down the axis, and then we took the critical angle and worked out how far that would be. Okay? And that gave us so many meters per kilometre. The slow rays travel so many meters more for every kilometre of fibre. You just divide that number of meters by the speed of light and you'll get the number of nanoseconds of dispersion per fibre. Right? But the problem with that was it was very primitive. All we were taking into account was total internal reflection. Okay? Unfortunately, there are other processes taking place. Light, as you know, diffracts from the source. So coming from the laser, the light would diffract. Some of it would strike the boundary right around in a cylindrical pattern and be reflected back towards the center, towards the axis again. That's all we've catered for so far, the reflection. And having reflected back, the reflected wavefronts would interfere. There's three processes going on together there. Now I can demonstrate, I think, if I can remember what I learned down in County Clare. If you listen up. higher pitch out there. Okay? I'm exciting a vibration of the goat skin there. I'm exciting a higher order mode out here. Higher pitch. What the difference between the two situations is, in this case, the center of the skin is vibrating in and out. There's a maximum here, and the vibration dies away towards the edge, towards the boundary. Whereas in this case, I'm exciting a ring here. And there's probably no vibration somewhere around here, midway. And then there's a lot of vibration in antiphase at the center. Okay? So we have vibration and vibration in the opposite phase, and nothing in between. So we've got the fundamental mode and a higher mode, which has a higher pitch. Exactly the same thing is going to happen here, because the cylindrical symmetry is the same, and the standing waves created by the interference of light coming back from the boundary. It's a circular boundary as well, or a cylindrical boundary. They're all coming back together, and they should create a similar pattern to that. Those patterns we just call cylinder functions for obvious reasons. So what had to be done was incorporate all of these effects and take a refractive index profile and work out what dispersion it causes. So to do that, we need the wave equation. This is a full approach now to solving the problem. It's just the operator del squared. That's just the rate of change in space, d2 by dx squared plus d2 by dy squared plus d2 by dz squared. And that is related to the double rate of change with time of the light field psi. The other parameters are index, permittivity, and permeability. Now, it would seem obvious that the simple version of del squared will not be the best approach here. We've got cylindrical geometry here. We go down a distance z, travel out a distance r, and swing around in the polar direction by an amount of phi. So our cylindrical coordinates are r, phi, z. And from your maths, it's straightforward to show that the double derivatives in cylinder space looks like this. It means you've got to take the second derivative with respect to r, the first derivative with respect to r, second with respect to phi, second with respect to z. All of those are easy to do, because you'll see now why. We'll make, as usual, with a differential equation like that, as best and intelligent a guess as we possibly can. Because it's a cylinder, there should be radial symmetry, f of r. Additionally, there should be what we call azimuthal, or polar symmetry. In other words, if there is a bright ring corresponding to a standing wave or mode of the fibre, it's possible that the bright ring would be bright, dark, bright, dark, bright, as you go around 360 degrees. Okay? Well, that would correspond to some kind of a cosine periodicity. So cosine with respect to phi. And we put an integer in there to tell us how many times are there bright and dark spots as you go around the ring. Okay? And finally, we have a wave propagating, e to the I omega t, is propagating with time. Omega is the angular frequency, 2 pi f. F is 200 terahertz. All right? Minus beta z is propagating away from the origin. You're looking back to the origin from your position z. And you're looking back having departed away at a rate beta. Beta is the propagation constant. That's what we're looking for, beta. If we can find the biggest propagation constant and the smallest one, we can calculate the dispersion between the fast and the slow light. Okay, well now, as I said, it looks maybe cumbersome, but it's actually quite straightforward, because to do these derivatives are easy enough. For example, you differentiate the cosine, your nu will come out. Nu is called the azimuthal mode number. It's the number of bright spots as you go around in the polar sense. Right? And then it'll come out a second time because you're differentiating it a double. So you get a nu squared. When you differentiate this, the omega comes down, and then again, because you're doing it twice, you get an omega squared, you get a beta squared. So you get these jumble of parameters that I'm going to show you in a minute. It's quite straightforward differentiation. But to complete the process and find the values of beta, there is a trick that you can use. And it's a trick we've actually already used a few pages back. We can compress space logarithmically. Remember we did that earlier on. We had an axis where there was 10 to the minus 1, 1, 10, 100, 1,000. Okay? That was a log axis based 10. Here we do the same. We compress our space into a logarithm a natural log base e. So we convert from R space to X space. And that just makes the solution of the equation far easier. The people who did that first, with this kind of situation crops up regularly in the physical sciences. And in one situation, Wenzel, Kramers and Briwan decided to adopt this approach. So now we apply it to optical fibre, and we still call it the WKB method. Alright, that double differentiation brings out these things, beta squared and all of the rest. And it turns out that all the solutions for the optical field psi, which are, we call them the modes of the fibre, they're the guided patterns. These are standing wave patterns just like on my boron there. Okay? And they travel down the fibre at the rate beta, which we're looking for. Okay, it turns out that in order that the standing wave result be valid and be oscillatory, rather than decaying exponentially, they're the two possibilities. You can have e to the minus something, or you can e to the iota something. Right? When the iota is there, all the something must be real in order to give a standing wave solution. All right? If it's not real, there's another iota there, and you have iota by iota, you have e to the minus 1 times everything, and you have a decaying light. So to get standing waves, it turns out that this jumble of parameters that comes out of the differentiation, n squared, k squared minus beta squared, must be bigger than this. This came out of differentiating the cosine, the nu, and then the nu again. All right? N of r is the refractive index profile. K is just 2 pi over lambda. It's related to the omega in the e to the I omega t equation. All right? So, for that, these parameters, quantities to be bigger than these, the trick we can do is, and it helps us visualize the light in the fibre. We can draw a graph of this. Now, what does it look like? N of r is some kind of a graded profile. If you square it, it still looks like a graded thing. And if you multiply it by 2 pi over lambda, well, you've fixed your lambda, your wavelength. It's 1.3 or it's 1.5 microns. So all of that, and the whole thing is pulled down by beta squared. So it all looks like, to all intents and purposes, the refractive index profile. Okay? In the core and the cladding. Whereas the other quantity is just a 1 over r squared graph. And we all know what they look like. It's dashed there. An integer squared over r squared. Now for this quantity to be bigger than this, that solid graph must be uppermost. So all of the light is guided in this region here, from here to here, from R1 to R2. Inside R1 or outside of R2, you're not satisfying the condition that the phase be real. You'll have 2 iotas and you'll have an exponentially fading light pattern. So here we have the ring that we got on our boron. It stretches from R1 to R2. And in the center there's no light, it's dark in the center, and it's dark outside of R2. Now the next thing we can do is we can say, but remember there are different modes with different parameters beta that travel at different rates down the z-axis. So if we make beta smaller, what's going to happen is this graph moves up. All right? The solid graph moves up as beta gets smaller. Right? And eventually, when beta is small enough, the two graphs separate entirely. Alternative, think of this cartoon-wise if you can. If beta goes the other way, if beta gets bigger and bigger and bigger, we're pulling the graph down, and eventually that part goes below the axis, and finally, eventually, the whole graph goes below the axis. When the whole graph goes below the axis, there's no intersection R1 and R2, there's no light guided. So we have two conditions. When the graph comes above, too high up, or the graph goes too far down. There's a maximum beta and a minimum beta. And it's 3 or 4 lines as an exercise in the book to show what those two max and min values are. By the way, all of the exercises given in the book, the answer is at the back. Every line of the answer is there at the back. If you have difficulty doing it. But this is quite an easy one to show. It's just a case of, for example, if this point here, the center, goes below, you get the N1K going below the axis, and that's where that comes from. But you can try it yourselves, and if not, go to the back. What this approach is showing is that there are mode patterns, and we can calculate R1 and R2. So, like on our boron, we could have a fundamental mode, bright and B is bright, merging out to dark. Or we could have bright, dark, several rings. Or within some of the rings, we could have bright, dark, bright going around as azimuthally. Okay? And what determines the number of rings is an integer which would give the symbol mu. That's the radial mode number. And what determines the number of spots is nu, the other integer. So between mu and nu, you have two integers which define every mode of the guide. And all of them have beta values ranging from N2K to N1K. This is exactly what the Glogen-Markatili team did. They put n of r with different shape factors, gamma, into the wave equation. They solved it by the WKB method, and they worked out what are the modes, okay, and what is the beta value. The beta value could be calculated once you knew the two integers, nu and mu. So the end result of the WKB analysis is what's called the eigenvalue equation. It's the equation which tells you beta once you define those two integers. Okay, so there's two integers for each mode. We call them the LP modes, and you put the two integers as a subscript, LP subscript nu mu. All right. If we draw a graph of nu against mu, we get a set of dots because they're integers. Okay, and it turns out there's a line along here, shown here, which corresponds to beta, and you could keep moving beta out until you get to the maximum permitted beta. We just calculated that; it's N1K. You can stop the line at that stage, and now you find you have a maximum nu and a maximum mu. Now if we count the dots, we've got the number of modes, we think. Turns out you're close to the number of modes. You have to actually multiply that number by 2, because when you started with the wave equation, you said cosine of nu phi. You could equally have said sine of nu phi, and you get an equally valid set of solutions to the wave equation. Okay. So, because the sine and the cosine need to be both added in together, you get double that. Another contributor is the fact that you can have a vertical polarization or a horizontal polarization of the LP modes. So that's another factor too. So when you integrate underneath that line, that's what we're doing here. Integral of mu d nu gives us the area, which because they're integers is the number of modes. You then multiply the answer by 4 to get the total number of guided modes. Now again, that takes a page or a page and a half in the text, and 1 or 2 of the steps are given as exercises, and if you're not happy about getting through it, you can go to the back and the full computation is there. Okay? But the end result is that the number of modes depends on the shape factor as shown there, okay, multiplied by a quantity. And the quantity that appears in the result is a quantity that crops up all over the place when we analyse the cylindrical fibre. And because it's cropping up all over the place, we give it a name. We call it the V parameter. So V is just defined as N1, that's the index at the centre, the axis, 2 pi over lambda, that's K, the radius of the core, that's A, root of 2 delta. Remember, delta is a small number, it's less than 1%. N1 minus N2 over N1. Okay, so we can tidy up the whole result by observing that, gee, this thing is all cropping up all over again like we've seen so many times. So the number of modes depends on the V parameter squared. Now if you put 2 extremes, infinity and 2, into that equation, you get these interesting results. For a step index fibre, by the way, when you put gamma into infinity, you remember what you do there, you just divide by gamma above and below. So you'll have 1 over, that'll be a 1, plus 2 over gamma, 2 over infinity is naught. Right? So to insert the infinity, that's the way you do it. And put in the 2, you'll just get 2 over 2 into 2 plus 2, a quarter. Very important result. Step index fibre has twice as many modes, possible modes, as graded index. The exact number depends on, what exactly is the index, what is the difference in the indices, and what is the wavelength you're using, and what is the diameter of the fibre. Because each mode comes out of the eigenvalue equation with its own beta value, this means that all the modes carry equal power. They're all equally valid solutions to the wave equation. That means there's twice as much power in this fibre as in the graded index. So our improvement in a bandwidth of 10 to 100,000, what it's costing us is half power, 3 decibels in our loss budget. Well worth it. Well, another thing that would have occurred to the teams in the various labs throughout the 70s, 80s and early 90s was, why not just get rid of all of the modes except the fundamental one, that one that we had in the Bowron where it was vibrating in the centre. And there's a nice, neat, simple pattern as well. Nice Gaussian bell, actually, of intensity. The trouble was, it was difficult enough to align step index fibres with the precision required, not to mind graded index fibres. And now, in order to get a monomode fibre where only the fundamental mode travels, we would have to reduce the radius considerably. That put huge alignment, had huge alignment implications for mechanical engineers more than anything else, making connectors that align within a micron or less, and splice machines which splice 2 fibre reels together within a less than a tenth of a micron perhaps. So the actual mechanical difficulties delayed the introduction of monomode fibre. People were very happy to rip out the step index and insert graded index in the 80s and 90s. And it was easy enough to do because the cable is pretty narrow, pretty small in diameter, and it would even fit between the gaps of the old copper cables. Copper cables are maybe 20 times bigger in diameter There was plenty of space to draw in the new fibres. Anyway, if we do our calculation, we had it there, the number of modes of half V squared. You note that V depends on A and lambda, so you're going to have to reduce A squared once you've settled on the wavelength. And the end result is that when V is less than this number, there's only one mode left. Some of you will recognize that number. It's related to the fundamental Bessel function, which is the fundamental mode of the fibre. Okay, so you'll come across it in other telecommunications theory. Anyway, V less than that gives us just a single mode. Notice, by the way, that because there's a wavelength dependence here, when you work out what is the diameter of single mode fibre, if you now start to change the wavelength, say you're working in C band, 1.5 microns, and you say, I'm going to try it at 1.3 microns, S band for some other reason. Well, what happens then is if you go back to N, you find a second mode appearing. So there is a wavelength for every optical fibre called the cutoff wavelength, and you must not go shorter than that wavelength or it becomes multimode all over again. In actual fact, it's the back of the book, you don't have to worry about it, but there's a kit you can use to measure modal dispersion in fibre. And I discovered the trick they were using, the people who manufactured the kit, was they were actually providing a transmitter which was shorter than the cutoff wavelength. So they were using single mode fibre, but the laser was just shorter than the cutoff wavelength, so it had become multi-mode, but not too multi-mode, just enough for a fourth year experiment or something to be able to measure the modal dispersion. Okay, now what we've got at this stage is we've eliminated the modal dispersion of the LP modes, because we've only got the LP01 mode, as it's called. Nu is 0 and mu is 1. It's the fundamental mode. However, thus far we have ignored some other effects taking place. I was actually looking for my old LP in the attic yesterday. I couldn't find it. Pink Floyd, Dark Side of the Moon, which shows a glass prism and light going through it and breaking up into all the colours. Fortunately, I couldn't find it, but you can remember anyway what chromatic dispersion is. Okay? Different colours travel at different speeds, and that's demonstrated here. This is dispersion in nanoseconds per kilometre, and it turns out that down here near the visible, reds travel faster than blue. I say red and blue, I mean long wavelength and short wavelength. And out here in the infrared, the reverse occurs. And at that critical wavelength, 1.3 microns, they're all in step. So that's why the first fibre installations were at 1.3 microns. It was to minimize chromatic dispersion. And then they got on and they did everything we've just calculated about the multimode dispersion. Okay? So chromatic dispersion goes through naught for SiO2 at that wavelength. And then it goes negative. And it's negative out at our new wavelength 1.55 microns, our 1980s and 90s lasers. The other dispersions we ignored was the profile and waveguide dispersions. Okay. The profile and the waveguide dispersion is just like what happens in a microwave waveguide. It's related to the dimensions of the guide. And both of those remain positive. So the dashed line is the other two. So this picture demonstrates all of the dispersions. We're using monomode and we're using step index at this stage. And modal dispersion is gone. What remains are these three. Something occurs to us. Chromatic is negative, but the other two are positive. Can we trade one off against the other and get zero? And that's what we do. We trade them on, we adjust the waveguide and profile somewhat, okay, so that it exactly cancels chromatic dispersion, and that happens exactly at 1.55 microns. That would seem to give us the ultimate optical fibre, the greatest bandwidth distance possible. So we call it dispersion shifted because we've shifted the dispersion minimum out to the loss minimum. We're getting both effects at the same time. To do it, you need to work out, you need to go back to your latest crop of PhD students and ask them, can you start modeling waveguide dispersion for us? And work out what waveguide pattern and profile pattern would we need to get exactly a positive dispersion that cancels this. And we have another bunch of PhDs out of that. Turns out, type of profile might be something like an M shape. Finally, one more thing that can be done. We now have dispersion shifted fibre at the minimum loss wavelength, and we're getting close to the total bandwidth capacity of our carrier at 200 terahertz. But now we think, well, what about using a bunch of lasers, all in the same fibre? Okay? And we can do this. The center laser would be at 200 terahertz, and then we could separate the others by about 50 gigahertz. And by doing that, you can fit about 100 wavelengths into the C band. You just need to be able to grow lasers with slightly different band gaps, right, to give you exactly the right member of this comb. That's called band gap engineering. It's quite an achievement. It's working out the solution of the Schrödinger equation in the crystal, working out the exact energy levels, and what alloy mix must I use to get a slightly different fraction of electron volt of band gap, and that will give me the right wavelengths. So there's another bunch of PhDs in doing all that band gap engineering, solving the Schrödinger equation in the crystal. Okay, so we can now in this way multiply up the capacity of every single fibre by 100 channels. They're all independent of one another. They won't interfere with one another travelling down the guide. They all have their own standing wave solutions, and they keep to themselves. You could do a lot with this. These systems are being installed as we speak. You could say, I have a customer in Dublin, Microsoft, and they have a massive capacity requirement to their headquarters in California. We'll assign that channel to them. We'll provide them with bit error rates of 10 to the minus 12. We'll give them their own wavelength channel, and we'll charge them the earth for it. We'll get rich. Or you could even go further than that. As the demand for capacity changes, you could use one of these. Now this is a tunable laser, and we've used these for years in our research labs in this university and have multiple publications on them. But essentially, the laser chip, the tiny chip that you saw in this picture at the beginning, sitting on top of its gold heatsink, that tiny chip is further subdivided. One of the sections of it has got a diffraction grating, which works like the prism on Pink Floyd's album cover, except it's doing it with a diffraction grating instead of a prism. And it reflects back a single wavelength. And when you inject current into that grating, you flood the grating with carriers, and there is an effect on the refractive index of the grating. Okay? And that changes the reflected wavelength. So we have the possibility here to electronically control the output wavelength rather than simply band gap engineering. You do band gap engineering to start with to get your center channel. And after that, you would flood the sections of the laser with carriers, slightly change the refractive index, and tune the laser to one of the other colours, 50 gigahertz apart. Now that has the possibility for dynamic wavelength division multiplexing. And the D there stands for dense wavelength division multiplexing. You can actually bring this down even further to 25 gigahertz spacing. Okay, what could we do? We could say, look, it's past midnight. Everybody in Microsoft Dublin have gone home. However, there's a need for capacity in Hong Kong. So we could reassign their channel to a customer in Hong Kong for 8 hours or whatever, dynamically. Of course, you can imagine that going on throughout the city, throughout the nations of the world, that as demand changes all the time, you can dynamically reassign the channels using these tunable lasers. You could even do one further thing, and I'll finish on that. You can build a little grating like this into a section of an optical fibre. Okay? And that fibre Bragg grating, as it's called, will transmit some wavelengths and reflect others. So you have a way to separate out the channels. You could arrive from Dublin to Cork, where there's a spur out to the transatlantic optical cables, and you could transmit the New York bound channels and reflect passively with a fibre Bragg grating the Cork bound channels. Okay? You could furthermore use the wavelength as the address of an IP packet. For the duration of the IP packet, you tune to a particular wavelength, and then your fibre Bragg gratings at all the nodes in your network will reflect some of the channels and transmit the others totally passively without you doing anything. All you had to do was select the wavelength of the IP packet at the beginning. The wavelength is the address. And it's all happening dynamically. So this is the future of these fibre optic networks. I don't see that happening for another 2, 3, 4, 5, 6 years maybe. But everything else has happened that I've spoken about up as far as DWDM. Thanks.